will start to discuss some new topics compared with the previous series of lectures. So as you can see from the title, we will use manifold learning techniques to study nonstationary time series. And so that is the rough schedule for this part 2 lecture, and it will maybe span for the coming 10-20 lectures. So we'll start from motivating problems, which we will discuss today, and we will have some overview about machine learning, manifold learning, and then we will talk about how to apply manifold learning algorithms for ultra-long time series analysis. And we will also cover some random matrix theory and some theoretical results of manifold learnings, differential geometry, and also discuss some kernel sensor fusion, spatial temporal analysis, and so on. So the first slide will be a recall of the motivating example. So this is a fetal electrocardiogram. So as we have discussed before, this is the topic about caring about your baby's health status when you are during pregnancy. So what you can do is you can put a lead, ECG lead, on the pregnant woman's abdomen, and you record the ECG signal. And in this ECG signal, if you pay attention, you will see there will be some big spikes. Those are maternal ECG, maternal heartbeats, and there are small bits. Those small bits are fetal ECG. And our goal is trying to decompose the signal, this transabdominal maternal ECG signal, into fetal ECG and maternal ECG. And what we have done so far is the following. We know the ultimate goal is to decompose the signal, maternal ECG, into maternal and the fetal ECG. And this can be understood as the single channel blind source separation, because you only have one channel, but this one channel is composed of two signals. And these two signals have some complicated structures. For example, you see that what we want is the decomposition, but we run into several challenges. For example, you only have one or few channels, so that you cannot apply the traditional ICA, independent component analysis techniques. Second, you see that the oscillations, they are very spiky. They are very spiky in time domain. So in the frequency domain, it will be of broad spectrum. And both maternal ECG and the fetal ECG have the same property. So in the frequency domain, you cannot just apply the traditional bandpass filter technique to do the decomposition. Third, you can see that the signal usually is noisy and even have artifacts. And the noise is not stationary. You can see this is clean, relatively clean here, but suddenly it becomes very noisy. And then you have the frequency, amplitude, oscillatory patterns, everything changed before, as you saw before. So how to achieve the decomposition? So what we have done so far is, in the previous lecture, we talked about this D-shape algorithm. And in this D-shape algorithm, we have shown you how to apply time frequency analysis technique to estimate maternal and the fetal heart rate. But once you get the fetal heart rate or maternal heart rate, what can you do to achieve the decomposition? That is the topic we haven't discussed so far. And if you have interest, the lecture is in the YouTube. So what we can do once we get the maternal heart rate is the following. Once we use a D-shape synchronous squeezing to get maternal heart rate or fetal heart rate, then we can apply the traditional peak tracking algorithm to get the location, precise location of maternal heartbeats and the fetal heartbeats. And what you do is you set up the instantaneous heart rate as the each point, and now you try to find all the points, locations of maternal bits, And the location of maternal bits ideally, it will give you as close as possible information as the instantaneous heart rate. So if you take a look at this P function, it tells you that over the two consecutive detected bits, which we don't know where they are, we hope that the location will give you as close as possible information about the heart rate that you get from the D shape. And then you combine this P function with the magnitude of the signal. We want it to be as large as possible as peaks. And then you just run some dynamical programming algorithm to optimize this function, and the result will be the detected fetal heartbeat. In this case, we talk about maternal heartbeats. And once we know the maternal heartbeats, then we can proceed to the next step. So, step 1 was apply D-shape synchro squeezing to get maternal heart rate. Second step is applying peak tracking algorithm, as I mentioned before, okay, to detect the location of maternal heartbeat locations. And then, what can we do to really achieve this decomposition? That will be the topic we will cover by using the manifold learning algorithm. As you can see, we will convert a seemingly irrelevant data set, which is a time series, and we will convert it into a manifold learning problem and study the so-called manifold learning, decomposition and so on. And this is the first motivating problem. Then we will talk about the second motivating example, which is about deep brain stimulation. Okay, deep brain stimulation is a treatment technique right now that is very commonly used to treat patients with severe Parkinson's disease. Like in the end of the disease, the medical treatment fails, then the only choice, the only possibility we have to treat patients is by this technique of deep brain stimulation. And what you do is, it is easy to say, but it's very technical and difficult. In the whole world, there are not many places that can carry out this technique. And what you do is you will insert a needle, like you will open a hole on your scalp, and you insert a needle deep into your brain, and going through the thalamus and touch the area called subthalamus nucleus, and you will put a battery maybe below your clavicle, and this pulse generator battery will generate shocks, continuous shocks to stimulate your brain. And as you can imagine, you have to have a needle going through your cortex, going through your brain, which is not very fun. But that is the treatment that can be very, very efficient for patients in the end of the disease that cannot move or have a lot of troubles living. And this treatment can return their life into normal. Patients who receive this kind of treatment can even go climb mountain themselves without others' treatment. So this is a very important technique treatment. And this is if you zoom in this subthalamus region, you will see this is a subthalamus nucleus, which is very, very small, tiny, and you have the lead and so on. So it counts on a lot of techniques to achieve this kind of installation. And then what is the manifold learning problem? Manifold learning problem associated with this deep brain stimulation? It is actually the following. As I mentioned, the pulse generator, it will generate this kind of spiky trend, which is about 130 hertz. Okay, to stimulate your brain. And our question usually is, how will your brain respond to this stimulation? We know that, a patient's behavior is improved and becomes better, but can we know more? And how can we know more? Then we need to study the brain wave. And the background here is a small fluctuation-like signal. This is the brain wave. This is the local field potential. But when you turn on the stimulation, as you can imagine, the stimulation will lead to some kind of spiky artifacts in addition to the local field potential. So our question is, will it be possible to remove those spiky artifacts so that we can study the local field potential and better understand our brain during stimulation? That's the question. Okay, and the reason we care about it is because it is 130 hertz. So you may say, hey, it's 130 hertz. So by Nyquist rate, we can still understand quite a lot of information below 130 hertz, right? But for local field potential, people have known that quite a lot of information is actually hidden in a higher frequency spectral higher spectrum instead of just below 130. So we want to explore more about it. But because of this spiky oscillatory pattern, the contamination of the stimulation artifact is not just in 130, it will be also in 260, 390, all the multiples. And so this has been a problem that kind of bothered researchers for a while, and there have been quite a lot of algorithms trying to resolve it. For example, the top one, this is the raw local field potential signal, and there have been several algorithms. For example, this is moving average subtraction, and this SI is subtraction and interpolation, I remember, and this is Hempel filter. And what you do in MAS is very simple. What you say is, oh, because the stimulation is so similar, right? It just spike. Then what we do is, oh, we just take maybe 10 consecutive spikes and evaluate the average and view it as a pattern and subtract it from each stimulation artifact. And maybe we can recover the local field potential. Okay, and the subtraction and interpolation is very simple. As you can see, this is the result. What people do is we just know, oh, there's a stimulation, so we just remove this period and then run a linear interpolation, And as you can imagine, it will miss a lot of information. And the Hempel filter is actually something very much like SI, but in the frequency domain. So there are several algorithms people have done so far to try to remove the stimulation artifact so that we can study the local field potential, but unfortunately, the results are not very good. If you zoom in, you will see that all algorithms still have quite a lot of unpleasant artifacts remain. So you need a new algorithm to improve it. And the manifold learning algorithm that I will mention in a bit will be aiming for this purpose. We'll try to remove those stimulation artifacts. And that is the result in the frequency domain. As you can see in the frequency domain, the original raw data, you can see there's a lot of spikes, right? And all those spikes have their own meaning. For example, this is 130 stimulation artifacts, and there will be 60 hertz, which is about 60 hertz is what? It's 60 hertz. Yeah, so this is 130, 260, and so on. This is stimulation artifact, and doesn't function very well. What? Okay. Doesn't want to respond. Okay, and this power 9, 120, 180, and so on. This is a power 9 stimulation, power 9 artifacts, and you have a lot of aliasing. Okay, because the sampling rate, although the sampling rate is high, but because the stimulation is very, very spiky, so it has aliasing coming back from the high frequency to low frequency. So you can see a lot of artifacts that generates trouble when we try to analyze this kind of signal, both in time domain and frequency domain. So the signal processing goal and the challenge here is Again, we want to recover local field potential and study brain dynamics during deep brain stimulation. This okay. This one is non-function. So the high frequency oscillation behavior, that is what we want to study of the local field potential during deep brain stimulation. Okay, and the local field potential behavior, a lot of things, interesting things. For example, you have stimulation, evoked resonance neural activity, and so on. There are several topics we want to study, but first thing first, we need to remove the stimulation artifact. And several challenges, just like before. Usually you have one channel or just few channels. In the local field potential, usually in one lead, there are maximally three channels. So the traditional ICA cannot help. And as you can see, it's very, very spiky, so the spectrum is very, very broad. And the local field potential itself is actually non-stationary. It behaves like a pink noise because it's a brain wave. It has a very, very strong long-range dependent structure. And then how to study this kind of noise, this kind of signal as noise, because we want to recover stimulation artifact, right? So local field potential can be viewed as noise. Okay? And the oscillatory pattern, as you can just visualize it by your eyes, it changes from time to time, right? It changes from time to time. Okay, and this is something you can imagine, like if you are given a delta major, very, very spiky delta major, and you have finite sample to it, then how much can you recover the signal? Right? Mathematically, you cannot recover it at all, right? But in data analysis, sorry, we cannot just write down a delta major and do analysis. We need to really see how the computer can get. So again, this is a single channel blind source separation problem. Because you only have one channel, and you want to decompose the signal into pieces. Okay. So to study all this kind of data, I will quickly introduce a model called the wave-shape manifold model. And this is something that may remind you the wave-shape function we discussed before in time frequency analysis. And yes, we will discuss wave-shape function, but this time we will study wave-shape function from the perspective of manifold. So that can be viewed as a new model for time series analysis. And later on, I will connect this new model from differential geometry perspective and link it to stochastic differential equation perspective, so that it's linked back to the time series analysis. Let's see what we have first from the data analysis perspective. So I will use this ECG signal, which is a very standard medical signal, as an example. So for the ECG signal, you can see that usually there's a sinoatrial node here, and there is atrioventricular node here. And what you have is in SA node, it has a self-paced regular passing, and after the passing, it will generate some stimulation path, okay, and buffered in the AV node. And then once the AV node is buffered, the electrical activity will go through the partition fiber to stimulate the stroke of the ventricle. So that is kind of repeating again and again and again. So what you can see is, you can view at time tj, there is an impulse stimulation from SA node. And this SA node impulse stimulation will cause some kind of response of the heart, and you record it again and again. So at each time, Tj, you have sinoatrial node stimulation, and at another time, you have another stimulation, so that you get this similar pattern, repeat, and repeat. And this pattern actually reflects the electrophysiological behavior of the heart. So the ECG signal if you view it from this perspective, you can rewrite it in the following way. There will be several electrophysiological activity. I denote it as xj, and this xj is an L2 function, and it is some kind of compactly supported around 1 heart cycle, and you just put it at time tj, and you put it again and again. Every time at time tj, you stimulate a cardiac activity called xj, and then you add some noise. So this is something you can rewrite the ECG signal and try to study what's going on. And it has a good property that it can help you to capture the time-varying wave-shape function that we discussed before. In the very beginning, this ECG signal, this patient has a normal heart, normal sinus rhythm, but in the second half of the ECG signal, the patient developed myocardial infarction. You can see there's ST elevation, and this developed myocardial infarction is reflected in the time-varying changing behavior of electrophysiological behavior. So that XJ is on the left-hand side and on the right-hand side, they are different. So it captures two pieces of information. First, you have physiological variability. Okay, that is this heart rate variability. Second, you have the phase, you have the shape or wave-shape function that describes the local electrophysiological dynamics. And then where is the manifold? What you do is look at this signal again. We take two pieces of information, facts, about our physiological dynamics into account. First is there is a variation. Everyone has a variation. There is a dynamics inside our body. But this dynamics is not crazy or totally all random. It follows some rules. So we can just take this rule into account and parameterize the wave-shape function by a low-dimensional manifold in this way. That is, for every every electrophysiological dynamics, you view it as a point in L2 function. You view it as a point in L2 space. Okay, and all the points can be parameterized by a low-dimensional manifold. And definitely, it is just a very rough model. It's just a very rough model. It can be very, very complicated, and we can dig into it and better study what's really going on. And in this parameterization, you see that the temporal relationship actually is forgotten, but it will be taken into account to study the dynamics in a bit. And now we may ask, why is this new model? Because remember, in the first part of the lecture, we spent quite a lot of time discussing the wave-shape, time-varying wave-shape model, like this one, adaptive non-harmonic model. That is, we try to modify the one periodic function by Fourier series and try to modify the Fourier series relationship by time-dependent parameters and so on, and put some assumptions. Then why is it not good? It is not good just because of this slowly varying instantaneous frequency and amplitude modulation model, because it forces us to consider only those time-varying wave-shape functions that changes slowly. That is, we are not able to control or analyze signals that has very fast time-varying wave-shape function. And that is the example you can immediately see from biomedical signals. This is a signal from a subject that has arrhythmia. And he has two different kinds of arrhythmia. First, there's a PVC, and this is PVC. This is one type, and there's another type of PVC. So you can see that the heart is beating, and repeating itself. Most of the time, you can see that it's normal sinus rhythm, normal beat. But from time to time, you have arrhythmia called premature ventricular contractional PVC. And this PVC, if you want to quantify it using wave shape, this adaptive non-harmonic model, sorry, you cannot do it because you can see that the wave shape function changes too dramatically from one cycle to another and back to normal. So the previous model cannot allow us to do too much. And time frequency analysis, in this case, may not be successfully applied. So it has limitation. That is why we try to develop this manifold learning-based algorithm. And for this kind of signal, if you think from the manifold setup, you will see that the manifold we are considering is actually has you can view it as two disconnected components. One component is for normal sinus reason. Another one is pathophysiological status, which means your heart is problematic. So that is disconnected, and you just have sampling points jumping in between disconnected manifolds. Another question is, can we leverage this model and do something? And this is another example. Okay, so the frequency changes very, very fast because this is an atrial fibrillation. A patient with atrial fibrillation, and it also this is atrial fibrillation or no, this is atrial fibrillation. Okay, whatever. And so it's not really normal. Its ventricular activity is normal for some bits. These are normal, but this is abnormal. This is abnormal. Okay, so so the frequency also changes very fast. So for this signal, sorry, it is not possible to use the traditional time frequency analysis models. And there are more examples. If you know, you have some background knowledge about ECG signal, then you may see that this is called QT interval, and this is called R interval. And this QT interval and R interval, they are actually not linearly related. So because it's not linearly related, the traditional model, again, doesn't really hold. Because the traditional model, you need to have the idea of linear stretching of the wave shape manifold or wave shape function. So wave shape function varies according to time, and this variation needs to be captured better. So the final slide is a very simple connection in between. Oh, hello. Okay. So it is a very simple connection in between the adaptive non-harmonic model and this manifold model. So if you remember before, we have the wave shape function S, and you can imagine that suppose you have a wave shape manifold. Then what you can do is you can stretch it and scale it. Okay, and the stretch it and the scale it can be viewed as two-dimensional parametrization. And these two-dimensional parametrization can give you some kind of a map of this U set into a L2 space. Okay, and this can be viewed as a one-chart manifold. So this is a very, very simple idea to describe, what do you mean by this time-varying wave shape manifold and the wave shape manifold model? Because this wave shape manifold model can be understood as just stretching, which describes instantaneous frequency, and the scaling, which describes amplitude modulation in a very high-dimensional space. And even there is a theorem which you can consider adaptive non-harmonic model that satisfies A, S of phi, and if you make some basic assumptions about amplitude modulation and the phase, then you can truncate the signal into pieces, and for each truncated piece, you can prove that it actually can be well approximated by a two-dimensional manifold. Okay, and so on. Okay, so this is for the first part.